This video is going to review complex number arithmetic. We're going to do a bit of revision of the notation that we use when we're talking about complex numbers, and then I'll do a quick summary as well as to how to use an argand diagram. So I'm going to start off by doing a bit of set theory as to how we describe complex numbers. So the set of all complex numbers are given by this blackboard capital C, which can be described like this. So it's the set of all numbers of this form, a plus bi, where a and b are real numbers, and I is this imaginary unit that squares to make -1. Okay, it's worth noting now as well that complex numbers live in 2D space. So when we plot them, we put them into 2D space here, which is called an argand diagram. You've got the real axis here horizontally, and then the imaginary axis here vertically. Let's first of all plot a complex number to see what we're doing. So let's plot a number here. Let's call this z. And I'm going to make that 3 plus 4i. So when you write these components down, we're thinking of this number here. This is the real part of our imaginary number. So the real part of z is 3. And then 4 is what we call the imaginary part of z, and that's going to be 4. I is, of course, being this number over here. Okay, so that's our number plotted. It plots just like a coordinate does because our 3 is our real component and 4 is our imaginary component there. So now what we can do is we can get the modulus of our complex number. And if we know that the components are 3 by 4, we can easily use some Pythagoras to work that out. So if you know your Pythagorean triples, you'll know that then the hypotenuse length is 5, so that's the modulus of z is 5. Okay, all right, so let's firstly write down the formula that what we've done there to get the modulus. So if z is a plus bi, then you've got absolute value is this hypotenuse length, which is given by square rooting the sum of the squares of the components. That's going to give you a number. Then we can also talk about the conjugate to z, which is going to go down here. So the conjugate to z, which is z bar, or sometimes z star, is what you get when you negate the imaginary parts and change its sign. So z bar in this case will be 3 minus 4i, which, as I said, will reflect in the real axis because of that change in sign there. So going back to here, if z is a plus bi, then our conjugate, which is either z or z star, that's given by a minus bi. Okay, and that's the conjugate. Great. Okay, thirdly, when we draw a complex number in the plane, we tend to want to talk about its argument, which in this case will be the angle given in here, if I'm talking about z. So theta is this angle that we get when we rotate anti-clockwise around from the positive real direction. And we tend to want to put that in a particular range of values. So the argument of z, written like that, is this angle theta. And then the range of values is typically this, minus pi less than theta less than or equal to pi. Bearing in mind that these two are given in radians. And the conversion into degrees is given by this. So you've got pi radians is 180 degrees. So that's a nice thing to remember as to how to convert. If you've got a nice multiple of 180, you can refer to 180 as pi and then get the same multiple of pi. Okay, so going back to our example case, if z is 3 plus 4i, then we can work it out using a bit of trigonometry. So in our example, we've got tan of theta is 4 over 3. Okay, a sketch is very helpful in working out which way around this goes and what to do with any minus signs. And I'll leave it to you to work out what theta is by doing the inverse tan of 4/3. Okay, so we can maybe add that to our list of formulae here. We've got these two, and then we've got the argument of z is going to be something like inverse tan of b over a. But depending on the quadrant that you're in, it might be slightly different. So what you want to do is check the quadrant that we're in with the sketch. Okay, there might be some minus signs there that you've got to to sort out if you're on, particularly from the left-hand side of the plane. Okay, perfect. So let's maybe look at some examples and some exam questions, and I'll leave you to do some extra practice. Okay, so first of all, I'll do a few of these, and I want to point out something that we've discussed using a theorem with polynomials, and then I'll leave you to do some yourself. So question 1 says, here's a complex number. You've got w, which is this quotient here, minus 9 plus 3i over 1 minus 2i, and we want the modulus and argument of this number. So the answers are given here, but I'm going to show you what's going to happen, and then you can see what I've done. So modulus, first of all. So let's firstly take our complex number w, and we want to ideally express that in our usual form here as something plus something times I. And if we can do that, then that gives us a way to draw a sketch. So let's start by writing our complex number as it is. And then to make this into a real denominator, to get it into this form, I'm going to multiply by the conjugate of the denominator on top and bottom. So that's going to be 1 plus 2i, top and bottom. And then I can FOIL out the top and the bottom here. So on the top, I've got to do, the first ones make minus 9. The outers make minus 18i. The inners make 3i. And then if I times the imaginary parts together, then 3 times 2 is 6, and I squared is minus 1. So that's going to make minus 6. Okay, on the bottom, this is the difference of squares, if you like, except when you've got i's involved, it will become the sum of squares. And you can check that this makes 1 squared plus 2 squared. Okay, there's a nice way to multiply conjugates together like that. Okay, let's tidy up. So on the top, we've got minus 15, and then minus 15i. And on the bottom, we're going to get 5, because that's 1 plus 4. And then simplifying at the end, we've got minus 3 minus 3i. Okay, so we've simplified our complex number. If I draw a sketch now, then I can get these two things that I need to finish the question. So here's my rough argand diagram. I know that if both of these are negative, it will be down in the bottom left quadrant. So here's my complex number. And I know it's gone 3 to the left. I'm just putting the positive values for their lengths just for now. And 3 that way. Okay, so here's where w lives. I can now get the argument first, so I'll do that. And that's going to be the square root of 3 squared plus 3 squared. I could have maybe done that as minus 3 squared and minus 3 squared, but that's good enough. And then that's going to give me root 18. And then by splitting up my surd, I can make root 9 root 2. And that's 3 root 2. Okay, as given up there. Okay, for the argument, bear in mind that I'm supposed to have an argument between minus pi and pi, which means that if my complex number is in the lower half of the plane, it makes sense to go around clockwise in order to get this negative side for my arguments. So I'm going to go around this way to get my angle here. This is going to be my argument. And to do that, I'm going to need to work out, firstly, what this small part here is in the triangle, and then do some very easy geometry to get theta out of that. So looking at the triangle that I've got, tan of alpha, the small angle, is 3 over 3, which is 1. Now, if you know that these components are equal, you can probably easily tell what the angle is going to be, but I'm going to do it properly. So tan of alpha is 1, and then you inverse tan on that, and you're going to get 45 degrees. But I want that in radians, so that's going to be pi over 4 in radians. Okay, bear in mind pi is 180, so a quarter of that will be my 45 degrees. Okay, so my argument then is going to be what's left over from 180 degrees. But remember, because I'm going clockwise, which is the counter direction, the negative direction, I need a negative for my angle there. So the argument of w is this angle theta, but that's going to be minus 3/4 pi. Okay, and what I've done there is I've done pi radians minus my alpha, and then made that negative. Okay, brilliant. So that's the first one done. I'll maybe do a couple more, and then I'll leave it to you to do some yourself. Question 2 is solving this quadratic, but you'll notice this is quite a difficult one because we've got complex coefficients here. We've got this I in our middle coefficient here. Okay, so complex coefficients are slightly different because it means that we're not allowed to use a particular theorem that we've been using when we've been solving polynomials. So I'm going to make a note of that. So if the coefficients are purely real, which is what we've seen so far. Okay, so only if they're real, then the roots of the equation will come in pairs, in conjugate pairs. So z is a root if and only if z bar is a root. Okay, so we've been using that quite freely when we've been solving polynomials. But this time we've got complex coefficients, so actually this isn't allowed to be used. Okay, that isn't going to be true if the complex coefficients are what we've got. Okay, and you'll see from the answer here, these roots here aren't complex conjugates. Okay, the real parts have been negated, but not the imaginary parts. So we've got to solve this a bit more, with a bit more ingenuity. So seeing as it's a quadratic equation, I think the best thing to do is probably use the formula. I mean, the clue's given in the box here, but that's what I would do. I don't really have a nice method of solving it, particularly if you've got i's in the middle. So let's maybe just use the formula. Okay, so bearing in mind that these are going to have complex numbers in, my a is going to be 2, the coefficient of z squared. My b is going to be minus 2i, okay, the thing in front of z, and c is going to be minus 5. Putting that together gives me z equals negative b, which is negative 2i, plus minus, and then the square root. And then I've got minus 2i, which is my b all squared, minus 4 times 2 times minus 5. And that's all divided by 2 lots of a, which is 4. Okay, let's tidy up. So minus 2i is 2i, plus minus. Okay, now I've got to be careful with this because I get a triple negative. So minus squared will disappear. So it's really just 2i all squared. And then I squared gives me minus 1, so this will be minus 4. Okay, check that carefully yourself if you're not sure. Then double negative here gives me a plus, and then 4 times 2 is 8, times 5 is 40. Okay, that's divided by 4. Last little bit of tidying, so this is 2i plus and minus root 44 divided by 4. I'm now going to break this square root into things that I can simplify it with. So 2i plus minus, this is going to be, sorry, it's not 44, is it? It's 36. What am I doing? There we go. Sorry, 36. Well, I've got to be careful with minus signs there. So that's 36 over 4. So I can make that into a 6. And then because I've got a common factor of 2 everywhere, I can divide the top and bottom by 2. So this is I plus minus 3 over 2. I then want to write that in its real and imaginary part form. So that's going to be firstly plus or minus 3 over 2 at the beginning, and then it's plus I over 2 there. And then we're done. And those are the two roots. Notice finally as well, as we've discussed, these are not conjugate pairs, and that's because the coefficients weren't real. Okay, so that formula didn't apply. Okay, great. That should hopefully be enough for you to get on with. I'll set some on Show My Homework for you to have a look at, and then if you've got any questions, please let me know. Otherwise, best of luck. See you soon, Year 12. Thanks very much.